So this is the third video going through the details from global to local and index bound for umbilic points on smooth convex surfaces, paper by myself and Wilhelm, which recently posted on the archive. In this video we want to talk about what is section 2 in the paper, which is this concept of a totally real blow-up. Now, a totally real blow-up, we're terming it this. It has many similarities, I guess, to the standard blow-up. So let's recall that for the standard blow-up in algebraic geometry, so when you blow up, in particular, a complex surface. So suppose you have a four-manifold with a complex structure, referred to as a complex surface, and then you blow it up at a point, and essentially what you do is you connect some with the CP2. Topologically, this is how it changes, and you replace, the idea is that, another way of looking at it is you replace a point by the lines, the complex lines through the point. Complex lines through the point. Now, in what we do, it's similar in some sense. We still have a complex surface, but in fact what we have is a real surface sitting inside this complex surface. And when we blow up a point on this surface, what we do is we connect some with an RP2. And in analogy with what we have up there, you replace the point on the surface by the real lines through the point. And when I say real lines, I mean real lines on this surface, right? So it's just an S1 through the point. Through the point. Now, of course, here we do not change the ambient space, unlike standard blow-up where you're changing your ambient space. Here we're just changing, we have an embedded surface and we are replacing it by another embedded surface without changing the ambient space at all. Now, the claim that we have, and this, I guess, is in proposition, I think it's 2.1, proposition 2.1. This is all section 2 of the paper. Is that what you do when you do that, you can do it in such a way that this is, if it starts out being embedded, that it remains embedded, so you don't introduce any self-intersections in doing it. And secondly, if the point you blow up, if a point is a hyperbolic complex point, so a hyperbolic complex point is one with complex index -1, so your index is -1. In the case of it, this would be an umbilic of index -0.5 if we were to interpret it in for TS2. If this, it is removed. In other words, you can smooth it out so that it becomes totally real. It kills this complex point, hence the name totally real blow-up. Okay, so this is the claim. So let me try and explain a little bit about how we would go about showing that and explicitly what the details of the construction are. Of course, the paper contains all of the details that will be required. So let's start out with, let's look at these hyperbolic complex points. So this is a simple enough model that we can use. So we're working, it's all local, so let's just think about this in C2, although of course it could be any complex surface. So let's take C2 and let's take coordinates psi and eta as their coordinates that we standardly use. And let's look at the following surface. The surface, which is given by, it's a graph, psi bar squared. Now, if you look at that surface, you can ask, well, it's a real surface. We want to know, does it have any complex points? To see, has it got complex points, what you do is you take the del bar of eta, which would be 2 psi bar, and ask, where does this vanish? So this is clearly 0, if and only if xi is equal to 0. So it has a complex point at the origin, complex point at 0. And moreover, you can see that the winding number, as you go around this point, this goes around in an opposite direction, so its index of this 0 is -1, as we say. So this is a hyperbolic complex point. Now, ultimately we're going to glue it to something, this RP2, that's not a graph. So in fact, we usually go to non-graph coordinates. So we don't think of it as a graph anymore. So let's just look at a slightly different parameterization, which will, so you'll see it's exactly the same thing, and squared. So that's fairly straightforward. So there's your hyperbolic complex point surface with an isolated hyperbolic complex point. Now, we want to connect it to RP2. So let's think about RP2. RP2 is a sphere with antipodal points identified. In fact, it's probably easier to think of it as a hemisphere. So if you can think of it as a disk where you identify opposite points on the boundary. And what we're going to do is we're going to take this, we have a real surface here, we're going to cut out a disk here, and then glue them together. So this will be your connect sum of your original surface with an RP2. Now, what model do we have for an RP2? Well, an RP2 is easy enough to construct in these coordinates. So let's parameterize it as follows. Eta equals mu bar squared. So here we see parameterization of a surface again. I claim it's an RP2. The range of the values is, say, a little bit less than 1, less than or equal to mu less than 1. When the norm mu equals 1, of course, then you have a circle, but it's double covered because of this mu bar squared. So this is a double cover of a circle. So double cover. So this is your this is the antipodal map acting on your boundary. Okay, now so it's not hard to see that you can take higher order terms and you can glue these two together along a radius 1 minus epsilon. Here your epsilon is just this, if you like, that distance there. And you can just smooth it out. We do it explicitly in the paper, and you can certainly look there for the full details of that. Of course, the situation we're interested in is, of course, that your M is in fact TS2. So all this goes through for any complex surface, in fact. But in this proposition, we use this proposition for TS2, and your surface is an S2. In fact, your surface is a sphere, and you do this K times. We do this cancel K complex points. Now, let's see this. This is all in TS2, but in fact, we have this relationship between TS2 and the lines in R3, which of course is the basis on which we even are motivated to do this construction. So in fact, you can interpret this whole picture in R3. So let me go through that now. So first of all, let's start out with our surface, which is, we showed this before in the earlier video. This is a complex point, a surface with a complex point of index -1, or an umbilic point of index -0.5, using our translation back and forward between the two. And what I've done is I've cut a disk out of this surface, and then I've just drawn in the normal lines. Now, of course, the normal lines on this curve will form a ruled surface. So a curve of lines is a ruled surface. So this is our ruled surface. Now what we want to do is, we're in TS2, we're filling this in by an RP2. And what we're going to see in R3 is that we're going to fill it in by a 2-parameter family of oriented lines. And what we will do in the picture here is we will take radii of this RP2. So if you look at your RP2 and you see it as looking, as we said, something like this, with identified here and here, we're going to take circles. Now, you've cut your disk out, this is where you're gluing it on, and we're going to take circles all the way around here of as you go up to the double covered circle in the middle. So when you take that, what you find is a sequence. You start out, here's your oriented normal lines. I've taken the lines out just for ease of vision. And then as you move in on your Gauss radius, your ruled surface starts to form a kind of threefold kind of cusp. It comes in together, it starts to cross over each other further and further, until eventually it double covers a cylinder. So this cylinder here is your S1 of RP2, this double covering. So you can really see this RP2 double covering this cylinder, this double covering on your S1 on the boundary in the space of oriented lines. Okay, now let's come back. So okay, there's no problem with that. Let's just mention one thing, which is this cancellation of complex points. How do we know that we're going to cancel any complex points? Well, it's not too hard to see. If you take, well, we mentioned Lie's formula, so let's bring that in here. So Lie's formula says that the number of complex points, the index, sum of the indices of complex points, so these are complex points, is the Euler number of the tangent bundle of your surface plus the Euler number of the normal bundle of your surface. Okay, so with that then let's look at what happens when you connect some with an RP2. Well, when you connect some with RP2, your surface, the Euler characteristic in fact goes down by 1. So in fact it'll be your tangent minus 1. And on the other hand, in the setting we're looking at, if you take the normal bundle and you connect some with RP2, in fact the Euler number of the normal bundle of the original surface now, and you end up adding 2 to it. Okay, so how can we kind of see this 2? Well, let's look at the picture in R3, because again we always have this in this setting to see to try and reinterpret these things. So let's just look in R3. If you take a sphere and you look at, say, the lines, the oriented lines coming out of the sphere, all directions, and suppose we wanted to see, this will give you in TS2, this gives you another sphere. Suppose I wanted to find out what's the Euler number of the normal bundle of this. Well, one way to do it would be to perturb it a bit, and if we perturb it, we will end up with it intersecting in a number of points, and then you count the number of intersections with sine, and you'll get the Euler number of the normal bundle. Well, here we have a natural perturbation, which is just to translate the surface. And if we translate this surface, of course, suppose we translate in this direction, well, these lines are going to move, and there's not going to be any common normal lines anymore, but the common normal line will here and here will have 2 points of intersection, and so we see that the Euler number of the normal bundle for the sphere is in fact 2. Okay, now what we do is not this, but in fact we've connected an RP2. So let's think about this RP2. Well, as we saw, you end up with this kind of a hole, and instead of a single line there, you end up with a circle, this flat cylinder, the whole way around here. And now if you do the same thing, you still retain those 2 intersection points, but in moving the circle off itself, of course, it's going to catch in 2 points. If you were to move it a little bit, the lines, the rulings will intersect in 2 more points. So what you end up with is an addition of 2 in the self-intersection, or equivalently an addition of 2 to the Euler number of the normal bundle. So putting all this together, what you see is that putting these in on the right hand side here is the number of complex points, so the sum of the indices of the complex points, is going to increase by 1. And this is precisely what cancels the index minus 1, the hyperbolic complex points, which we use this process then to remove these complex points. Okay, in the final video we will look at the global arguments, which give us the final result, that the index bound that we claim.